Section 7.4 is about graphing polar equations. Now, we're going to begin by starting with this equation here, which is r equals 4 cosine of theta. So, we're going to keep it in polar coordinates, so we could have also changed to rectangular coordinates and sketched the graph in that way in terms of x and y, but again, that's not the purpose of this section. So, let's start by giving my angles that I'm going to use, and we're going to create a table in polar coordinates, which means in terms of theta and r, which is the radius, r and theta. Okay. Right here, the radius is going to be calculated by the equation 4 cosine of theta. So, it says right here that we're going to calculate it in radians. However, on my graph it's in radians, but to make the calculations a little bit easier, I'm going to be using degrees, for my calculations. So, I'm going to start with the first quadrant, 0 degrees, my special angles, 30 degrees, 45 degrees, 60 degrees, and 90 degrees, which is 0, pi over 6, pi over 4, pi over 3, and pi over 2. And let's calculate the radiuses. So this is going to be 4 cosine of 0 degrees. Let's keep in mind that cosine of 0 degrees is equal to 1. So that's 4 times 1 gives me 4 as an answer. So that means that the first point, it's going to be a radius of 4 at an angle of 0 degrees, or 0 radians, meaning that it's going to be on a circle of radius of 4 at an angle of 0, means on the polar axis, which is this line, the x-axis. So we're going to have 1, this is radius of 1, circle with radius of 2, circle with radius of 3, and circle with radius of 4. Next, let's make the next calculation. 4 cosine of 30 degrees. Let's remember from before, cosine of 30 degrees is equals to the square root of 3 over 2. But if you estimate the square root of 3 over 2, it is approximately equal to 0.9. Okay, it is an estimate. So that means this is going to be 4 times 0.9, which is going to be approximately to 3.6. So my second point tells me this is a circle with a radius of 3.6 at an angle of 30 degrees from the polar axis. Angle of 30 degrees is my pi over 6. So we're going to look at this angle, we're going to locate the point at a radius of 3.6. So this is radius of 1, radius of 2, radius of 3, and radius of 3.6 is going to be a little bit more than 3.5. The next one. Now we're going to make the next calculation. It's going to be 4 times cosine of theta, which theta is 45 degrees this time. Cosine of 45, let's keep in mind, it is equal to the square root of 2 over 2. If we estimate this using a calculator, this is about 0.7 approximately. So then this is the same as 4 times 0.7, which is going to be approximately 2.8. So that means that this point is going to be located on a radius of 2.8, on a circle of radius of 2.8 at an angle of 45 degrees from my polar axis. So 45 degrees is right in the middle right here on my first quadrant, and a circle of radius of 2.8 will be radius of 1, radius of 2, 2.8. It's almost on a radius of 3 circle, a little bit before getting to that, somewhere here. Next one. Then we're going to calculate 4 times cosine of theta, which in this case theta is 60 degrees. Now cosine of 60 is equal to 1/2, which is 0.5. So 4 times 0.5 is going to be 2. So this one is going to be a radius of 2, a circle of radius of 2 located at an angle of 60 degrees from the polar axis. 60 degrees is my pi over 3 right here. So radius of 2 would be a circle of radius of 2, meaning radius of 1, radius of 2 at my 60 degrees is going to be located right here. And the last one that we're going to calculate here would be 4 times cosine of 90 degrees. Let's remember that cosine of 90 is equal to 0, so it would be 4 times 0, which is going to give me a 0. So this is going to be a radius of 0 located at an angle of 90 degrees. Now just keep in mind that it doesn't matter what the angle is. If the radius is 0, that will always be located at the origin. So, plotting those points all together, look at what that creates. That is going to create half of what we call a circle. Okay? So now we're going to create the other half. So what I'm going to do, I'm going to continue with my values. So now I'm going to continue with my second quadrant values, which is going to be 120 degrees, which is a 60-degree angle in my second quadrant, 135 degrees, which is a 45-degree reference angle in my second quadrant, 150, which is an angle of 30 degrees of reference in my second quadrant, and 180, which is on the axis, on the x-axis, okay, or polar axis. So let's evaluate this. So the first one is 4 times cosine of 120. So cosine of 120, it is basically the same as cosine of 60. Let's just keep in mind that in the second quadrant, cosine has a negative value. So instead of 0.5, it's going to be negative 0.5. So it's going to be 4 times negative 0.5, which is going to be negative 2. So that means that this one, it's going to be a point that is going to be located on a radius of negative 2, comma, at an angle of 120 degrees. What does that mean? 120 is this line right here, which is my 2 pi over 3. That is my 120 line. But if the radius of 2 would be located up here, but remember that when the radius is negative, it is going to be located in the opposite side of this line, which is on my fourth quadrant. This will be that 120 line, as you can see, but located at a radius of negative 2, meaning on the opposite side. Okay. The next one. Now we have 4 times cosine of 135 degrees. Cosine of 135 degrees, that is a 45 degree reference angle in my second quadrant. So that's a 45. So it's the same thing as this value, which is 0.7. But since it is on the second quadrant, remember that cosine is negative on the second quadrant. So it will be 4 times negative 0.7, which is approximately to negative 2.8. So what is this going to be? It is a circle of radius of negative 2.8 at an angle of 135 degrees. 135 degrees is my 3 pi over 4 right here. But if it's a radius of negative 2.8, it's going to go on the opposite side of this line, which is negative 1, negative 2, negative 2.8. It's going to be somewhere in here. The next one. Next calculation, it's going to be 4 times cosine of 150 degrees. That's 150 degrees is a 30 degree reference angle in the second quadrant. So cosine of 30, we said it was 0.9, which is the square root of 3 over 2. But in the second quadrant, it would be negative. So that would be 4 times negative square root of 3 over 2, which is negative 0.9. And that gives me about negative 3.6. So this is going to give me a circle of radius of negative 3.6 at an angle of 150 degrees. So we're going to go at 150, which is my 5 pi over 6. This is 150. But radius of negative 3.6 will be on the opposite side. Negative 1, negative 2, negative 3, and negative 3.6 would be somewhere in here. And the last value would be 4 times cosine of 180 degrees. And cosine of 180, it's going to be negative 1. So that's 4 times negative 1, which is equal to negative 4. So this is going to be a radius of negative 4 at an angle of 180 degrees. So 180 degrees will be pi right here. But if it's a negative 4 radius, will be on the opposite side, which is negative 1, negative 2, negative 3, and negative 4. And what you see is that it's going to go back and connect to this original point, starting point. So from here where we ended on the first half, it's going to continue to this point, then it's going to go to this one, then it's going to go to this one, and then it's going to go back to this one. And that is my circle. Okay, so there's two equations of circles that we can have for polar equations, and the two of them are r equals a cosine of theta and r equals a sine of theta. In this case, that value of a, which is what you see here, is always going to represent the diameter of the circle. As you can see, the diameter is 4 units long, okay, which is the number in the front. So my two equations are, let's go back, are these two. R equals a cosine of theta creates a circle. R equals a sine of theta creates a circle. Now look at one little observation. On the a cosine of theta, you know, it's gonna be basically from the origin, it's gonna be on the right side. You see, the circle is gonna go to the right side, my 4 units. And on the a sine of theta, from the origin, my diameter is gonna go up 8 units. Okay, that's the difference between those two. Next one. Now we have we could have also done one more thing. In this circle, if I would have wanted, I could have just done half of these points right here, and then use the definition of symmetry to basically sketch the other half, and that will be a lot easier. That's what we're going to look at next. How can we help ourselves with symmetry so that we can just sketch only partial piece of the graph and then just reflect it over some axis, depending on the type of symmetry that whatever equation has. The three types of symmetries that a polar equation could have are these three. Symmetry with respect to the polar axis. The polar axis, remember, as discussed in section 6.3, it is my x-axis. Now, when does that happen that we have an x-axis symmetry? Is when I replace a negative theta for the theta into my equation, and my equation does not change at all. If it gives me the original or the same equation back, then that means that the function or the equation has x-axis reflection, meaning polar axis reflection or polar axis symmetry. Okay, so you see, because negative theta would be basically a point compared to this one would be located on the bottom, which will be a reflection of that point onto the x-axis, which we call the polar axis. Second type of reflection is the reflection along the line theta equals pi over 2, which is my y-axis, basically. Okay, so y-axis symmetry happens like, for example, if I replace a theta with negative theta, you see that the point, it's going to be down here, but then also at the same time I'm going to replace the radius with a negative radius, and what that does is that it's going to make this point go on the opposite side, which is right here on this quadrant. So if I replace the radius with a negative radius and the angle and the angle theta with a negative theta, and it gives me the same equation back, the same original equation back, that means that that equation has y-axis symmetry, which is the same thing as symmetry along the line theta equals pi over 2. Third type of symmetry is symmetry with respect to the pole. The pole will be the same as the origin. This is the pole. Okay, and when origin symmetry means that it reflects over the y-axis followed by a reflection over the x-axis, or vice versa. Reflection over the x-axis followed by a reflection over the y-axis. That's what it means by an origin reflection. Okay, and when does that happen? If I just replace the radius with a negative radius, because if I do that, then this point is going to go on the opposite side, which is basically a reflection over the y-axis right here, followed by a reflection over the x-axis down here. Okay. Now, if we would have done that in this example that we did, then look at the first type of symmetry, polar axis symmetry. If I just do that around the polar axis, for the polar axis all I have to do is replace the theta with a negative theta. So if I do change the theta to a negative theta, what is cosine of negative theta equals to? Remember, cosine is an even function, meaning that cosine of negative theta is the same as cosine of theta. This equation gave me the original equation back, meaning that this function has polar axis symmetry or x-axis symmetry. So that means that if I would have just done the top half of this graph, I could have just reflected it over to the bottom instead of doing all these points. Next, let's go ahead and do that here. Check for the symmetry and then graph this polar equation. R equals 1 minus cosine of theta. So, first thing is that we're going to create a table for this. Well, before the table, we're going to check the symmetry. Let's do that first. Now, for the symmetries, first I'm going to check if it has polar axis symmetry, which is the same thing as my x-axis. Question mark. Polar axis symmetry. How do I check up for that? I replace my theta with a negative theta. And just keep in mind, since cosine is an even function, then cosine of negative theta is just the same as cosine of theta. So that is just going to become cosine of theta. And what do you notice? That it gives me the same equation back. So that means, yes, this equation has polar axis symmetry by definition. Okay. There might be more than one symmetry, so we'd rather check all of them just to confirm. Okay. The next one, it's going to be the symmetry about the theta equals pi over 2 symmetry over that line. Let's check for this. For this one, we have to replace r with the radius with negative radius and the theta with negative theta. We're going to change both. So what happens is that, well, first of all, if we want, let's do the even property first, which means that cosine of negative theta equals to cosine of theta. But then to get rid of the negative, we're going to multiply everything by -1 or divide everything by -1. And if I do this, what we're going to get is r equals to -1 plus cosine of theta. And as you can see, this equation is not the same as the original equation, meaning that doesn't automatically mean that this function, that this equation doesn't have symmetry along the y-axis. It means that it might or might not have symmetry along the y-axis. We cannot tell. Okay, just because this test fails doesn't mean automatically that the equation doesn't have that type of symmetry. It could be still that it has it, but we cannot guarantee it. Okay. The only one that is guaranteed is the polar axis symmetry so far. Last type of symmetry, which is my pole symmetry about the pole. So we're going to say pole symmetry, which is the origin. For that one, we're just going to change r to a -r. That's what we need to do. And if I change r to -r, same thing is going to happen. I'm going to have to divide everything by -1. And what we're going to get is -1 plus cosine of theta. And that is not the same as the original equation, meaning that doesn't mean that this equation does not have symmetry along the pole, meaning that reflects over the x and the y-axis, both of them. That doesn't mean that it doesn't have it. It could be or it couldn't be that it has it or not. So it is, it's not a guarantee. Okay. So the only one that we have as a guarantee is reflection over the polar axis, which is the x-axis. So we know that we're just going to create the half of it, and then we're just going to reflect it over to the other side, to the bottom. Or we create the bottom, whichever one appears first, and then we reflect it up to the top. So let's start with the information here. R equals 1 minus cosine of theta. So we're going to start with the 0 degrees. So R equals, I don't have to write dr. 1 minus cosine of 0 degrees. Cosine of 0 is 1, so 1 minus 1, it's going to give me a 0. Okay, so the first point gives us this. It's going to be a radius of 0 at an angle of 0 degrees. Anytime the radius is 0, it's going to be at the origin. Next one. We're going to do the 30 degrees. 1 minus cosine of 30. Cosine of 30, let's keep in mind again, it's going to be the square root of 3 over 2. But anytime we have the square root of 3 over 2, that is approximately 0.9. So this is 1 minus 0.9, which is going to be 0.1, approximately. We're just estimating it. Okay, so that means that this is a radius of 0.1 at an angle of 30 degrees. Meaning, radius of angle of 30 degrees is my pi over 6 line right here. Radius of 30 degrees, radius of 0.1 would be basically almost right here, still almost at the touching there at the origin, very close to the origin. So I'm just gonna kind of make those points a little bit less bold, because then we might not be able to see all the points. So the first one we said it was the origin. The next point, it was the 0.1 at an angle of pi over 6. So 0.1 would be a very small radius. Okay. Next one. Now let's calculate the 45 degrees. So if I do 1 minus cosine of 45, remember that cosine of 45 is equal to the square root of 2 over 2, which is approximately 0.7. So that's the same as 1 minus 0.7, which is going to be approximately 2.3. So that's going to be located on a circle of approximately a circle of 0.3, radius of 0.3 units at an angle of 45 degrees. So we're going to go at an angle of 45 degrees, which is right in the middle of the first quadrant, pi over 4, and it's going to be with a radius of 0.3. So somewhere in here. Next one. Now we're going to do the 60 degrees. So 1 minus cosine of 60 degrees. Cosine of 60 is equal to 1/2 or 0.5. So 1 minus 0.5, it's going to be 0.5. So this is going to be located on a circle of radius of 0.5 at an angle of 60 degrees. So radius of 0.5 at 60 degrees is pi over 3, and radius of 0.5 would be somewhere right here in the middle. Next one. Now we're going to do 90 degrees. So 1 minus cosine of 90 degrees, that is going to be equal to, cosine of 90 is 0, so 1 minus 0 is going to be 1. So this is on a circle of radius of 1 at an angle of 90 degrees. That's going to be on the y-axis, right here at a radius of 1. Then that's still not enough, because that's not even half of the graph yet. So we still need to continue with more angles. So I'm going to continue with my second quadrant, 120 degrees. So for 120, this is going to be 1 minus cosine of 120. 120 would give me a 60-degree reference angle in the second quadrant. Cosine is negative in the second quadrant, so that would be the same as cosine of 60, which is 0.5, but it would be negative. So cosine of 120 would be negative 0.5. So 1 minus negative 0.5, it's going to be equal to 1.5. So that's going to be located on a radius of 1.5 at an angle of 120 degrees. So radius of 1.5 at an angle of 120. 120 would be my 2 pi over 3, and radius of 1.5 would be in a circle between radius of 1 and radius of 2. Next one. 135 degrees. 1 minus cosine of 135 degrees. 135 degrees, it's going to give me a 45 reference angle in the second quadrant, which is the square root of 2 over 2, which is 0.7, but negative, because cosine is negative in the second quadrant. So that's 1 minus negative 0.7. It's going to be approximately 1.7. So this is approximately located on a circle of radius of 1.7 at an angle of 135 degrees. So pi over 135 is 3 pi over 4, which is this line. And on a radius of 1.7, it is almost on a circle of radius of 2, close to that. So somewhere here. Next one. Now we're going to do 150. So 1 minus cosine of 150 degrees. Cosine of 150, it is equal to the square root of negative square root of 3 over 2, because it's in the second quadrant. So it would be 1, and negative square root of 3 over 2 would be negative 0.9. So it's 1 minus negative 0.9, it is approximately 1.9. So this is located on a circle of approximately 1.9 at an angle of 150 degrees. So that would be on my 150 degrees will be the same as my 5 pi over 6. So radius of 1.9 will be almost getting to the radius of 2, so somewhere in here. And next, we're going to do 180. So we're going to do 1 minus cosine of 180, but cosine of 180 is equal to negative 1, so 1 minus negative 1 is going to give me a 2. So this is going to be located on a circle of radius of 2 at an angle of 180 degrees. 180 degrees will be pi. Radius of 2 would be on the circle of the second radius right here, so radius of 2 on the edge. That is basically, as you can see now, it connected half of my graph already. So if I connect all these points, this is what this graph is going to show us. Let me just make it more accurate. This is half of the graph. So what kind of symmetry did we find this have? It had polar axis symmetry, which is x-axis symmetry, meaning that all I have to do now is reflect this piece over the x-axis to create the other half. And as you can see, this graph is going to look kind of like a heart shaped, right? That heart shape, we can call it into different ways. We can call it a limacon or a cardioid. We're going to introduce those next. So these are the graphs of cardioids, or what we called the limacons. So there are several ways a limacon could be seen as. It could be seen as a limacon with an inner loop. Inner loop means that it folds, it creates like one little loop in the interior of the shape, as you can see right here. It could be that the cardioid is more in the shape of a heart, which is basically the one we just got right now. Okay, that limacon that has the shape of a heart, we call it a cardioid. Okay, so the third one is it could be that that my limacon doesn't have an inner loop, so it could be just like this. And basically the last one is with no dimple and no inner loop, so just almost looking to be vertical right here at the end on the edge. Those are different representations of what we call the limacons, but just the only one that we're going to give a different name would be the heart-shaped. If it's a heart-shaped, it's going to be called a cardioid. And when does a cardioid or a limacon happens is when we have an equation of the form r equals a plus b sine theta, or a plus b cosine theta, a minus b sine theta, or a minus b cosine theta. This is when we're going to have either a limacon or a cardioid. Next graph. Now we're going to graph this polar equation. Graph the polar equation, r equals to 1 plus 2 sine of theta. First, what we will be determining is symmetry. Okay, so we're going to see if this has any type of symmetry. Let's go through polar axis symmetry. To check for polar axis symmetry, what do is that we replace theta with negative theta. But sine of negative theta is equal to negative sine of theta, which this is going to turn this into a negative 2 sine of theta. As you can see, this equation is not the same as the original equation. So that means this graph might or might not have polar axis symmetry. We cannot tell yet. Okay. Second, we're going to do symmetry about the line theta equals pi over 2, which is the y-axis. To check for this symmetry, what do? We change r to negative r and theta to negative theta. Now, the first part, sine of negative theta is the same thing as negative sine of theta, meaning that this is going to change the sign, negative 2 sine of theta. But then to get rid of the negative r, we divide everything by negative 1, and that is going to give us r equals negative 1 plus 2 sine of theta. And what do we see right here? That this is not the same as the original equation, meaning that this equation might or might not have y-axis symmetry. So we cannot tell. Third and last type of symmetry is pole symmetry. Okay, so for this one, we have to replace r with a negative r. Then I have to divide everything by negative 1 to get rid of the negative in front of the r. So it gives us r equals to negative 1 minus 2 sine of theta. What do we notice? That this equation is not the same as the original equation either. So we cannot guarantee a pole symmetry either, which is the origin symmetry. So this equation might or might not have any of this symmetry, so we cannot guarantee it. So what we're going to have to do, I'm going to have to create the whole graph until until one point until my last point connects with the first point that I plotted at 0 degrees. Okay, so we're going to have to do it that way. So let's start with my 0 degrees, and we're going to go from there. So this might be a long one, so bear with me, because we don't have a symmetry guaranteed. So we're going to have to do all the points until the graph connects itself. So we're going to start with 0 degrees. So if I do 1 plus 2 sine of 0, sine of 0 degrees is equal to 0, so this is the same thing as 1. 1 plus 0, which is 1. Right? So that means this is going to be a circle with radius of 1 at an angle of 0 degrees. Will be right here on my x-axis, on the right. Okay. Second, 30 degrees. 1 plus 2 sine of 30 degrees. Sine of 30 degrees is equal to 1/2. So this is 1 plus 2 times 1/2. 1/2 is 0.5. That is going to give me 1 plus 1, which is going to be a 2. So that's going to be located on a circle of radius of 2 at an angle of 30 degrees. Meaning 30 degrees is pi over 6 right here, but on a radius of 2. This is my circle with radius of 2. Third one, 45 degrees. 1 plus 2 sine of 45 degrees. Sine of 45 degrees, again, is equal to the square root of 2 over 2, but the square root of 2 over 2 is approximately 0.7. So this is going to be approximately 1 plus 2 times 0.7, it would be about 1.4. When I add them, 1 plus 1.4 is going to be approximately 2.4. So this is going to be a point that is located on a circle of radius 2.4 at an angle of 45 degrees. So 45 degrees is pi over 4. radius of 2.4, this is radius of 1, radius of 2, 2.4 is almost 2.5, somewhere in here. Next one, 60 degrees. 1 plus 2 times sine of 60 degrees. Sine of 60 degrees is going to be the same as the square root of 3 over 2. And the square root of 3 over 2 is approximately 0.9. So if I evaluate it, it's going to be 1 plus 2 times 0.9. I'm just going to multiply it already. 2 times 0.9 is 1.8. So 1 plus 1.8, it's approximately equal to 2.8. So that's a point located on a circle of radius 2.8 at an angle of 60 degrees. 60 degrees is pi over 3 right here. So radius of 2.8 will be radius of 1, radius of 2, almost on a radius of 3. 2.8 will be somewhere in here. Next one, 90. 1 plus 2 sine of 90 degrees. So 90 degree sine of 90, it's going to equal to 1. So it's 1 plus 2 times 1. It's going to be 1 plus 2, which is going to be a 3. So this is located on a circle of radius of 3 at an angle of 90 degrees, which is on my y-axis at 1, 2, radius of 3. Then we're going to continue. Okay. Now I have to continue with my 120. So remember, we have to continue until the graph connects itself to this original point that we had first, because we don't have our symmetry guaranteed. Okay. So this is 1 plus 2 times sine of 120 degrees. Sine of 120, the good thing is that sine is positive in quadrants 1 and quadrant 2. So it gives me the same value in quadrant 1 and quadrant 2. Meaning that sine of 120 is the same as sine of 60, because 120 gives me a 60 degree reference angle in the second quadrant. So sine of 60 was 2.8, so this is going to be also 2.8. Okay. So this is going to be a point located on a circle of radius 2.8 at an angle of 120 degrees. That means 120 is 2 pi over 3. Radius of 2.8, this is radius of 1, radius of 2. It is almost located on a radius of 3. Okay. I want you to keep a close look at what we have comparing this side to the left side. Okay. Angle of 135. So it is 1 plus 2 times sine of 135. Sine of 135 will be the same as sine of 45. Basically, it is the same as this value right here, because it is a 45. Sine is the same value in the first and second quadrant, right? So 45, and this is also a 45, but in the second quadrant. So that would be the same as approximately the sine of 45 that we got, the 45 degree angle, which is 2.4. So this is going to be located on a circle of a radius of 2.4 at an angle of 135 degrees. So radius of angle of 135 is 3 pi over 4. Radius of 2.4 would be radius of 1, radius of 2, 2.4 would be somewhere in here. I want you to compare the right side to the left side. What can we see? Apparently, even though the y-axis symmetry failed to exist right here, remember that it's not a guarantee. We cannot say that it doesn't have it. It is just not guaranteed right here, but as looking at the picture, we can see that it does have y-axis symmetry so far. Okay, so that means that if I do the next point, which is 150 degrees, guess what? That's going to be the same thing as my 30 degrees, right? So if I do 1 plus 2 sine of 150 degrees, that's going to be the same as my the 30 degrees, which is 2. So that gave me a 2. So I mean, this is going to be located on a circle of radius of 2 at an angle of 150 degrees. 150 degrees is pi over 6. Radius of 2 would be radius of 1, radius of 2, located right here. The next one, 180 degrees. So 1 plus 2 sine of 180. sine of 180 is equal to 0. So this is 1 plus 2 times 0, which is going to be 1. So this is located on a circle of radius of 1 at an angle of 180 degrees, meaning right in here. Okay. So we are not finished because we have not connected it back to this original point. So we still have to continue on this one. But something that we knew is that I could have just done, once I did the 120 and the 135, we saw already that it was being reflected over the y-axis. So I could have just done the reflection. So now we know that it has y-axis symmetry, even though it wasn't a guarantee here. So once we get all the way to the left side right here, or the right side completely, we're just going to reflect it instead of doing the whole thing. So now we're going to continue with my third quadrant. My third quadrant, it's going to be an angle of, first of all, the 30-degree angle in the third quadrant is going to be 210. Okay, so that's a 30-degree reference angle. Okay, sine of 210 degrees, it's going to be the same as sine of 30 because it's a 30-degree reference angle, but remember that sine of in the third quadrant is going to be negative, the sine. So sine of 30 was 1/2, but in this case, since it is in the third quadrant, is negative 1/2. So it's 1 plus 2 times negative 0.5. It's going to be 1 minus 1, which is going to be 0. So that's going to be a radius of 0 and an angle of 210 degrees. What does that mean? Radius of 0 means it's going to be at the origin. Okay. So far, if you want, so that we don't get lost, we can already connect what we have. Because it starts right here, goes to here, then goes to this one, and then it goes to this point right here, it goes to this one, it goes to this one, and it goes to this one, and then it's going to go back to the origin, right here at the 210. At the 210 meaning right here. This is my 210 line. Right? It goes back to the origin. So, let's continue with my 225, which is a 45-degree angle in the third quadrant. 225. So I'm going to do that one. So 1 plus 2 sine of 225. Sine of 225 would be the same as sine of 45, but negative. Sine of 45 is the square root of 2 over 2, which is 0.7. So right here would be negative 0.7. So it's approximately 1 plus 2 times negative 0.7, which is approximately equal to 1 minus 1.4, which is approximately equal to negative 0.4. Okay. So that means this is located on a circle of radius negative 0.4 at an angle of 225 degrees. So 225 degrees, it's going to be my 5 pi over 4 line right here, but negative 4 radius will be on the opposite side, meaning right here, and negative 0.4 radius will be close to the 0.5, somewhere right here. So we continue with the graph. I'm gonna join the next point. You see, goes to this one. Okay. Next. Now we are going to create 240 degrees. So 1 plus 2 sine of 240 degrees. 240 gives me a 60-degree reference angle in the third quadrant. So sine of 60, remember, is equal to square root of 3 over 2, which is approximately equal to square root of 3 over 2 is 0.9 approximately. So, but it would be negative because sine is negative in the third quadrant. So it would be 1 plus 2 times negative 0.9. It will be approximately equal to 1 minus 2 times negative 0.9 is negative 1.8. So 1 minus 1.8 is approximately equal to negative 0.8. So this is going to be close to a radius of negative 0.8 at an angle of 240 degrees. 240 degrees will be my 4 pi over 3 line. But since it is negative 0.8, the radius, it will go on the opposite side, which is going to be right in here. And negative 0.8 would be almost at the circle of radius of 1, very close. So then this is going to connect to this. Next. And then we're going to go to the 270, which is going to be my on the bottom, right? 270, that angle. Let me extend this line. For the 270, we're going to do 1 plus 2 sine of 270. Sine of 270, it's going to be equal to negative 1. So this is going to give me 1 plus 2 times negative 1. That's going to be 1 minus 2, which is going to be negative 1. So that's going to be a radius of negative 1 at an angle of 270. So where is the radius or angle of 270? It's down here, 3 pi over 2. But since it is a negative 1 radius, it will go on the opposite side, which is up here. So, and I think this is as far as we need to get, because what did we know already? Even though it was not a symmetry here on the test, it was not guaranteed, but we saw from the graph that it was reflected over the y-axis. So what we can do is reflect this little curve that we see right here onto the y-axis, and it's basically going to create something like this. And this little curve right here reflected onto the y-axis, so it's going to curve right here. So you see that this still looks like a limacon. The only difference is that it is a limacon with one inner loop, which is the first type of limacon that we had in the definitions. A limacon with one inner loop. And right here we have to do it all the way until we could be able to see that there was a symmetry just by looking, you know, with our eyes, until we were actually able to see it, because the tests for the symmetry failed to exist. So right here we were not sure, we were not guaranteed any of the symmetries, but again, like I said, that doesn't mean that there is no symmetry. That means that it could be or it could not be that it has one of those symmetries until we actually see it from the graph. Okay? Next. So the next type of graph we're going to do is going to be this one. R equals to 4 sine of 2 theta. First thing is that we're going to check for the symmetries. So the first type of symmetry I'm going to do is the polar axis symmetry. Let's see if that exists. Polar axis symmetry means x-axis. To check for x-axis symmetry, all I have to do is replace theta with negative theta. And just remember my our even identities, even and odd identities. Sine of negative theta equals to negative sine of theta. So that's going to give us r equals to negative 4 sine of 2 theta. Okay, so that is not the same thing as the original equation, meaning that this symmetry is not guaranteed. Second, we're going to do the y-axis symmetry, which is theta equals to pi over 2 symmetry. How do we check for that? We replace r with negative r and theta with negative theta. So r with negative r and the theta right here with negative theta. Sine of negative theta is equal to negative sine of theta, right? So this is going to be the same as negative 4 sine of 2 theta. But then to get rid of the negative in front of the r, we divide both sides by a negative 1. And guess what? This is going to give us back the 4 sine of 2 theta, which is the original equation. Since this gave me the same thing as the original equation, that means that we have guaranteed that this equation is going to be reflected over the y-axis, which is the line pi theta equals pi over 2. Now we're going to check the pole symmetry. Pole symmetry means the origin symmetry. Okay, so we're going to do replace r with a negative r. That's what we have to do. So if I replace the r with a negative r, I don't have to put it in parentheses here, because it's not originally. Replace the r with a negative r, I have to divide both sides by a negative 1, and in this case you can see automatically that this is going to give us negative 4 sine of 2 theta. And that is not the same as the original equation, meaning that it is not guaranteed. The only symmetry that we have guaranteed is y-axis symmetry. Let's keep that in mind. Now let's get the points. We're just going to get the points on one side, starting from 0 degrees until we get the left side, either the left side or the right side complete, and then we're just going to reflect it over. Okay. So we're going to start with saying that since this, I just want you to be careful, because since this graph has a double angle, in order for us to get those special, to get those special angles, my 30, my 45, my 60, and my 90 right here, since it is a double angle, we're going to start using multiples of 15. That's why you see that originally I had divided it into 15s. 15, 30, 45, 60, 75, 90. We're going to use those multiples of 15 degrees only when we see an equation with a multiple angle, either a double angle, triple angle, quadruple angle, quintuple angle, or any of those. That's when we have to use those, so we can fill all the gaps of these angles, my 15, my 30, my 30, my 60, my 45, my 60, and my 90. We have to use multiples of 15 to get those gaps filled in. So we're going to start with 0. We're going to do 4 sine of 2 times 0 degrees. So 2 times 0 is 0, and sine of 0, it's going to be 0. So that's going to give me 4 times 0, which is going to be still 0. So that's going to give me a radius of 0 and an angle of 0 degrees, meaning that's going to be at the origin. Next, 15 degrees. 4 times sine of 2 times 15 degrees. 2 times 15 is going to be 30, so that would be 4 times sine of 30. And let's keep in mind that sine of 30 equals to 0.5 or 1/2. So 4 times 0.5, it's going to be 2. So that gives me a radius of 2 and an angle of 15 degrees. That means that it's going to be a radius of 2. 15 degrees is going to be located right at the pi over 12. And radius of 2, it's going to be right here. Next one. 30 degrees. 4 times sine of 2 times 30 degrees. It's equal to 4 times sine of 2 times 30. It's going to be 60. And let's remember that sine of 60 is equal to the square root of 3 over 2. But the square root of 3 over 2 is approximately equal to 0.9. So that would be approximately equal to 4 times 0.9, which is approximately equal to 3.6. So this is close to a circle of radius of 3.6 at an angle of 30 degrees. So 30 degrees is pi over 6. Radius of 3.6 would be radius of 1, 2, 3. 3.6 will be somewhere in here. Next, 45 degrees. 4 times sine of 45 degrees. Sine of 45 is equal to the square root of 2 over 2, and that is approximately equal to 0.7. So we're going to have 4 times I forgot the 2. Let me just go back. It was 2 times 45. So I'm going to erase this for now, so I can go back to this. So a sine of 2 times theta, which is 2 times 45. 2 times 45 is 90, so that would be 4 sine of 90, but sine of 90 is equal to 1. So 4 times 1 is going to be 4. So that's going to be a radius of 4 at an angle of 45 degrees. 45 is pi over 4. Radius of 4 would be 1, 2, 3, and 4. This is where the point is going to be. Okay. If you want to start looking at the shape as we go, you can start connecting it all together. So this is what the graph so far gives us. As you can see, that's what we have so far. Okay. The next one. Now let's calculate 60 degrees. This is multiples of 15. We're doing multiples of 15 because of the double angle. So it would be 4 times sine of 2 times 60. 2 times 60 is 120, so it's 4 times sine of 120. But sine of 120, it's going to give me the same as sine of my 60, right? Which sine of 60 was the same as the square root of 3 over 2, which is 0.9, so this is also 0.9. This is 4 times 0.9, which is approximately equal to 3.6. So this is a radius of 3.6 at an angle of 60 degrees. So 3.6, angle of 60, it's pi over 3 right here. Radius of 3.6 is 1, 2, 3.6. It's going to be somewhere in here. Okay. So I'm going to connect the next point so we can start looking at the shape as we go. This is what we have so far. Okay. Next one. Now we're going to go to an angle. The next multiple of 15 would be 75. So it's 4 times sine of 2 times 75 degrees. 2 times 75 is 150. So it's 4 times sine of 150 degrees. And 150 degrees, sine of 150 is the same as sine of 30. Sine of 30 was 0.5 or 1/2. So this is the same thing as 4 times 0.5, which is equal to 2. So this is going to be a radius of 2 at an angle of 75 degrees. 75 degrees is 5 pi over 12. So, and then at a radius of 2 would be radius of 1, radius of 2. So this is where it's going to land. So let's connect the next point so we can start looking at the shape as we go. This is where the next point is going to go. And the next one would be 90. So if I do 4 times sine of 2 times 90, 2 times 90 is 180, so 4 times sine of 180, sine of 180 is going to be 0, so that's 4 times 0, which is going to be 0. So that gives us a radius of 0 at an angle of 90. Guess what? That goes back to the origin. It's going to go back to the origin right here. Okay, so we know that this one has y-axis symmetry, but again, I'm just going to continue this a little bit further because I'm just going to tell you this equation is going to create what we call a rows. Okay, and the rows can have more than, like right here, if I reflect it over the y-axis, is going to create two petals. So the petal on the left side and the petal on the right side. But roses might have more than that. So what I'm going to do, I'm just going to continue to see if it's going to create another petal that is somewhere either on the third quadrant or on the fourth quadrant. That's what I want to do. Okay. Now we're going to continue with 100, and the next multiple of 15 would be 105. So if I do 4 times sine of 2 times 105 degrees, 105 times 2 is 210. So it will be 4 times sine of 210. And remember that sine of 210 is the same as sine of 30, because it's a 30-degree angle in the third quadrant, but it has to be negative. Sine of 30 is the same as 0.5, so this is negative 0.5. So if I do 4 times negative 0.5, that's going to be negative 2. So that's a radius of negative 2 at an angle of 105 degrees. That's what my original angle is. 105 is going to be my 7 pi over 12 line. But since it is a -2 radius, what does that mean? It's going to go on the opposite side. -1, -2. Oh, but there's a little change I have to do though, because it's my 7 pi over 12. 7 pi over 12 in the opposite side is here. -1, -2. I put it in the wrong place. There it is. So, if you continue, look what happens. This last point that we got, now it's going to go to this right here. Okay. Now, let's continue. What is the next multiple of 15? 120. So if I go to 120, then we're going to do 4 times sine of 2 times 120, and 2 times 120 is 240, so it's going to give me 4 times sine of 240, and sine of 240 is the same as sine of 60 but negative. Sine of 60 is 0.9, square root of 3 over 2, which is 0.9, so this is -0.9. So it's 4 times -0.9, which is approximately equal to -3.6. So that's on a radius of -3.6 at an angle of 120 degrees. What does it mean? 120, it's 2 pi over 3 right here on this side. But since it is a -3.6 radius, it's going to go on the opposite side. -1, -2, -3.6 radius will be located right in here. And you see that it's starting to take its shape. So you see that this is going to kind of create another petal of this rose. If we extend this, it's moving on to this side now. Okay? Now we're going to go to the next value, which is 135. That's the next multiple of 15. So it's 4 times sine of 2 times 135 degrees. So 2 times 135 is 270. So that would be 4 times sine of 270 degrees. So sine of 270, it's going to be -1. So that's 4 times -1, which is -4. So that's a radius of -4 at an angle of 135 degrees. So 135 is 3 pi over 4. Radius of -1, it is going to go on -4, I'm sorry, it's going to go on the opposite side, meaning -1, -2, -3, and -4. This is where it's going to land. So we're going to connect that next point, and you see it's starting to take its shape right here. The next point. Now we're going to do the next multiple of 15, which is 150. So 4 times sine of 2 times 150, it would be 4 sine of 300. But sine of 300, it gives me a 60-degree reference angle in the 4th quadrant. If it's a sine of 60 is the same as the square root of 3 over 2, which is 0.9, but in the 4th quadrant, it's going to be negative. So it would be -0.9. So it would be 4 times -0.9, which is approximately equal to -3.6. Okay, so this is going to give me a radius of -3.6 at an angle of 150 degrees. 150 degrees is going to be 5 pi over 6. Radius of -3.6 is going to go on the opposite sides, which is right here. -1, -2, -3.6. It's going to be somewhere right here. And we're going to connect that point to this. Last but not least, well, no, we have 2 more actually. The next multiple of 15, it's 165 degrees. Okay, so let's evaluate that one. And I'm going to extend this line because we need 2 more values, all the way to the 180. 165, so it would be 4 times sine of 2 times 165 degrees. That would be 4 times sine of 330. 330 is going to create a 30-degree reference angle in the fourth quadrant. So sine of 30 is equal to 1/2 always, but since it is in the fourth quadrant, it's negative 1/2. So it would be 4 times negative 0.5, which is going to be negative 2. So that gives me a radius of negative 2 at an angle of 165 degrees. 165 degrees will be my 11 pi over 12. That's 165. But since it is a radius of negative 2, it's going to go on the opposite side, meaning negative 1, negative 2, right here. And I'm going to connect it, and that is going to go back here, from here to here. Last but not least, we are going to do the 180, which is the next multiple of 15. And look what's going to happen. 4 times sine of 2 times 180 is equal to, 2 times 180 is 360. So 4 times sine of 360. Sine of 360 is equal to 0, so that's going to be 4 times 0, which is going to give me a 0. So that's a radius of 0 at an angle of 180 degrees. Okay, so radius of 0 means goes back to the origin. Okay, so my suggestion to you all is when you are graphing the polar graphs, use all the angles to create your table from 0 to 180 degrees. If it is a single angle, I just suggest you use the special values, special triangles, 0, 30, 45, 60, 90, 120, 135, 150, and 180. If my my equation has a multiple angle, whether a double, triple, quadruple, quintuple angle, or any of those, then go still from 0 to 180, but use all the multiples of 15 to make sure that the graph is complete. Okay, you can still do it with the multiples of 30, 45, and 60, but the thing is that you will see that you know, the shape will not be completely visible to you if you just use those. You're gonna get half of the points that we got right here, and without the other half, it might be a little bit more difficult to visualize the rest of the, how the curve goes. So what do we know now? That this equation has symmetry along the y-axis, meaning the theta equals pi over 2. So what I need to do is reflect this petal over to this side. So all of these points, I'm going to reflect them over to this side. So that's going to be basically right here. It's going to go all the way right here. It's going to go all the way right here. So my other petals. So let's go ahead and reflect our next petal for the symmetry. So it's going to go to this side, and then it's going to go back to, we're just going to estimate it. It's going to go back here. Then the other petal, it's going to go to this point, and then it's going to go back right in here. This is just symmetry. Kind of make a reflection from this side to the other side of the y-axis. So as you can see, this is a rose. We call it a rose with 4 petals. Now let's go through the definition of roses so you can see. We could have roses with 3 petals, 4 petals, 5 petals, or 8 petals, depending on the equation. Now these are some equations that we have set. If it is, the equation is r equals to a sine of 2 theta. 2 theta for the sine, it's going to create twice the number of petals as the angle. So twice the angle as the number of petals. So if it is a 2 theta, sine of 2 theta, it's going to create double, which is 4 petals, which is what we just got. And the length of the petal is going to be the number in the front of that equation, which, as you can see on the example we just did, the length of the petal from here to here is 4, because the number in front of my equation was a 4. Okay, so if I have an equation r equals a cosine of 3 theta, these are just some examples. A cosine of 3 theta. Okay, you see for the cosine, it's going to have the same number of petals as the angle. So it would be 3 petals. If it is r equals a cosine of 4 theta, for the cosine is going to create twice the number of petals. So you see it creates 8 petals. So the next one, it says r equals a sine of 5 theta, and that creates 5 petals. Summary: if the n, which is the angle, is a double, a quadruple, a sextuple, so when it's even, it's gonna have twice the number of petals as that angle. Okay, so if it is a 6 theta, it would create 12 petals. If it is 8 theta, it would create 16 petals, and so forth and so forth and so forth. Now, if that angle is odd, meaning that 3 theta or 5 theta or 7 theta, it's going to create that same number of petals. So 3 theta, you see, creates 3 petals. 5 theta creates 5 petals, and so on and so on and so on. And again, the length of the petal will always be given by the number in the front. That will tell you how big one of those petals is, how long, basically. Next and last, we're going to graph this polar equation. Graph the polar equation r squared equals 4 sine of 2 theta. First thing we're going to determine again is the symmetry. So, for the symmetry, what we have to do is first of all do the polar axis symmetry. So to check for that, we're going to replace theta with negative theta and see what we get. What happens here? Sine of negative theta is the same as negative sine of theta. So this is going to give us negative 4 sine of 2 theta. And this is not the same as this, meaning that we don't have a guaranteed polar axis symmetry. It could be that it has our x-axis symmetry as well as it could not be. We cannot tell. Okay. Second, we're going to do the y-axis symmetry, which is the pi over 2. Theta equals pi over 2 symmetry. So to determine the symmetry, we're going to replace r with negative r and theta with negative theta. So if I do negative r squared, negative r times negative r is positive r squared equals sine of negative theta is the same as negative sine of theta. And what do we see is that this equation again is not the same as this one, meaning that we don't have this symmetry guaranteed either. Last type of symmetry is symmetry along the pole. Pole symmetry means x and y axis symmetry simultaneously, which is the origin symmetry. That we can obtain it by just replacing r with negative r. Just that. And guess what? If I replace r with negative r, when I square it, it's going to stay positive r squared. So what does this tell us? That this equation is guaranteed that it's going to have pole symmetry. Symmetry along the pole. Meaning that it's going to reflect, once we get one side, like if I get something from the first quadrant, it's going to reflect onto the third quadrant. Because if I reflect something in the first quadrant onto the y-axis, then onto the x-axis, it's going to land in the third quadrant. If I have something in the second quadrant and I reflect it onto the x-axis and then the y-axis, it's going to be reflected onto the fourth quadrant. That is the origin symmetry. Double symmetry, x and y. Okay, so let's go ahead and get started with the table. Now this table is going to be kind of weird because we have the r squared. So to solve for r, we're going to have to do the square root to any all the values that we're going to get. Okay, and the thing is that since this one also gives us what's called a double angle, we're going to have to use multiples of 15 all the way from 0 to 180, like I told you, like I explained previously. So just to make it easy, what I'm going to do is this. Instead of putting r squared, because remember, I'm going to fix this. When I solve for r, what I have to do is I need to get the square root on both sides to get rid of the square, but then that's going to give me a plus or minus the square root of that. Okay, the square root of that. One thing that I can do is this. You can leave it just the way it is, or you can do one thing, because the square root of 4 is 2, so you can just do it as 2 times sine of 2 theta, if you want to. Otherwise, you can just do it like that. Okay. All right. So, if we want, we can just leave it like this for now. So let's go ahead and start with the evaluations. So remember that for each one of the values, we're going to have a plus or minus. And you know what the good thing is that if we get a negative number on the inside, like on the sign of whatever 2 theta is, if it gives me a negative, then we can stop, because anywhere that we get a negative square root, the point is not going to exist. It's going to be imaginary, as you learn in college algebra. So we're going to start with 0 degrees. So plus or minus square root of 4 times sine of 2 times 0. 2 times 0 is 0. Sine of 0 is going to be 0. So that's going to give me the square root of 4 times 0, which is still going to be square root of 0. And the square root of 0 is just going to be 0. So for this one, we get the point 0, comma, angle of 0 degrees, meaning that it's going to be at the origin. Next one. Now we're going to do multiples of 15. Why 15? Because I told you, anytime we have a double angle just like this, or triple angle, or quadruple angle, or any of that, you have to use multiples of 15 to have a more complete graph. So it would be more recommended. So, plus or minus square root of 4 times sine of 2 times 15. That would be sine of 30. So it would be plus or minus the square root of 4 times sine of 30. But sine of 30 is equal to 1/2 or 0.5. And 4 times 0.5, it's going to be 2. So this is going to be equal to plus or minus the square root of 2, but the square root of 2 is approximately equal to 1.7. 1.4, I'm sorry. So that means that for this one, we're going to have a radius of plus or minus 1.4 at an angle of 15 degrees. What does that mean? We have 2 points. One of them is going to be on an angle of 15, which is pi over 12, with a radius of 1.4, meaning 1.4, almost 1.5. And another one, it's going to be on the opposite side, because it's going to be in radius of negative 1.4, meaning negative 1, negative 1.4, somewhere in here. Okay, so we're going to have it in 2 sides. And you see that's my origin symmetry. You see that this gets reflected over the third quadrant. So it reflects over the x-axis right here, and then you reflect it over the y-axis, y-axis and then x-axis to create this other point. That's what we call the origin symmetry or pole symmetry. Next one, 30 degrees. Plus or minus the square root of 4 times sine of 2 times 30. 2 times 30 is 60. And let's keep in mind, sine of 60 degrees is the square root of 3 over 2. But the square root of 3 over 2 is approximately equal to 0.9. So that would be 4 times 0.9, which is going to be approximately plus or minus the square root of 3.6. Okay, And that, we're going to get the square root of that using the calculator. So for 3.6, if I get the square root of that, it's about 1.9. So this is approximately equal to plus or minus 1.9, meaning we're going to have a radius of positive 1.9 and negative 1.9 at an angle of 30 degrees. Hold on. Angle of 30 degrees. So 30 degrees is pi over 6 right here. Angle of radius of 1.9 would be 1 and almost 2, very close to 2, somewhere in here. And also negative 1.9 will be on the opposite side, negative on this same line, negative 1, negative 1.9. And that, you see, if you reflect this point onto the y-axis, it's going to go right here. Right here, yeah. And then if you reflect it right here onto the x-axis, it's going to go right here. That is my pole symmetry. Okay? So far I'm going to connect the points, the 2 points, the 3 points, from here to here to here, as you can see. Okay? And then we can also see that it happens on the other side, from here to here to here. You will see the shape of this one as we finish it. Next, now we're gonna do the 45-degree angle. Plus or minus the square root of 4 times sine of 2 times 45. 2 times 45 is 90. So we're gonna have plus or minus 4 times sine of 90. Sine of 90 is equal to 1. 4 times 1 is going to be 4, so plus or minus the square root of 4 is going to give me plus or minus 2. That means that this is going to be a radius of positive 2 or negative 2 at an angle of 45 degrees. Meaning that we're going to go at an angle of 45, meaning pi over 4 on this line. At a radius of 2 would be 1 and 2. It would be right here. And radius of negative 2 would go on the opposite direction. Negative 1 and negative 2. Okay, and let's connect those points so we can continue with the shape. So it's going to go to this point, and right here it's going to go to this point. Okay, now we're going to go to the next multiple of 15, which is going to be 60. So plus or minus the square root of 4 times sine of 2 times 60. 2 times 60 is 120. Okay, so it would be 4, the square root of sine of 120 is the same as sine of 60, because remember, in the first quadrant and the second quadrant, sine has the same values, right? So sine of 120, it's going to be the same as sine of 60, and sine of 60 is the same as the square root of 3 over 2, which is 0.9. So it would be again 4 times 0.9, and that is going to be plus or minus the square root of 3.6, and the square root of 3.6 is going to be approximately plus or minus 1.9. So this is going to be a radius of positive or negative 1.9, both at an angle of 60 degrees. So let's start with the angle of 60, which is pi over 3. Radius of 1.9 would be 1, and 0.9 would be somewhere over here. And radius of negative 1.9 will go on the opposite side, which is negative 1, negative 1.9. It would be somewhere here. So if we connect those points, this is going to go now to this right here, and this is going to go to this right here. Okay, we're almost close to the end. Now we're going to do 75 degrees. Next multiple of 15. Plus or minus the square root of 4 times sine of 2 times 75 degrees. 2 times 75 is going to be 150. So it would be 4 times sine of 150, but sine of 150 is the same as sine of 30. Sine of 30 is 1/2, which is 0.5. So 2 times 0.5 is going to be positive 2, and the square root of 2, it's going to be approximately 1.4. So it would be plus or minus 1.4, meaning that we're going to have a radius of positive 1.4 or negative 1.4 at an angle of 75 degrees. 75 is the same as 5 pi over 12. So angle of 1.4 would be 1.4. An angle of negative 1.4 will go in the opposite direction, means negative 1, negative 1.4, right here. And if we continue with the graph, look what it looks like. Okay, there you go. And the next one, we're going to do the 90. That's the next multiple of 15. Plus or minus the square root of 4 times sine of 2 times 90. It's going to be plus or minus 4 times sine of 180, but sine of 180, it's going to be 0. 4 times 0, it's going to be 0, and the square root of 0, it's 0. So that's just going to be 1 point. And the angle of radius of 0 at an angle of 90 degrees. Okay, meaning that both of these points, blue points, are going to go back to the origin. And that's when we wanted to, that's where we wanted it to go. We wanted it to go back to the original first point that we had. Okay, and that's the only thing on this one, because let me tell you what happens if I go a little bit further. Let's say, for example, 105. When I multiply it times 2, look at what you're going to get. You don't have to do this part. 4 times sine of 2 times 105, it's going to be 210. But the problem is, sine of 210 is the same thing as sine of 30, but negative, because it is on the third quadrant. So it would be the same thing as what we got for the 30, which is 0.5. Basically, it would be the same as this one. No, what is it? This one and this one, right? Which is going to give me 0.5, but negative 0.5. So it would be plus or minus the square root of 4 times negative 0.5, which is going to be negative 2. And what do we know about the square root of a negative number? It does not exist. What's going to happen if we continue all the way to 180? It's going to give me my angles in the third and fourth quadrant. My special values in the third and fourth quadrant for sine. And sine is always negative in the third quadrant or in the fourth quadrant. So, and the square root of a negative number does not exist. So this is basically all what this graph is going to show us. This graph has a name. It's called a Lemniscate. Okay, it comes from, basically, I believe it's from the Latin of ribbons. Okay, Lemniscate basically is represented by the word ribbon, and it looks like a ribbon, which is another way of looking at it is like an infinity sign. That's what a Lemniscate is going to look like. And this is the last graph that you need to make sure you're familiar with, which is called the Lemniscates. So whenever you have r squared equals a squared sine of 2 theta, or r squared equals a squared cosine of 2 theta, you see that the number right here was a perfect square, which was a 4. If it's a 4, a 16, even if it's not, just this, whatever number you have there, it can be a 5. It doesn't have to be a perfect square, but if it's a 5, then the square root of that number will always represent the length of one side of my Lemniscate, or one of the loops. So r squared equals a squared sine of 2 theta, and r squared equals a squared cosine of 2 theta. Both of them create a Lemniscate. This is going to be the end of section 7.4.